Well, it's time for a problem. H4. Let's do a pendulum problem. And let's say we have no friction. So this swings freely from this point up here. And if you want, you could, attach it to the ceiling there. And there's a ball, the bob. Ball's often called the bob. And we're looking at here an angle. We're going to release the ball. And then the bob is going to wind up down here as it swings. And then it's going to swing like this and swing back. This is the equilibrium position that if you let it hang there, it would stay there. So this is mass M. This is the length L. And the problem that we would like to do is what's the speed of the ball at the bottom? In other words, what is the velocity at the bottom? We want the formula. And we'll want to do one specific case where the M is 2 kilograms and the length is 1.5 meters and the angle is 90 degrees. So that's going to be one problem. Start it up here and let it go and it come down. And then for the second problem, let's go ahead and say, this is question 1, what is the velocity at the bottom? And then question 2 is, what is the formula in terms of the angle, depending on the angle that the velocity would be at the bottom here. So using conservation of energy, let's say before, kinetic energy plus potential before equals the kinetic energy after and the potential energy after. If I pick up this mass up to here, then it's going to be that length. See, if this were to hang straight down, that would be the length. So you're basically picking it up. If it's up here, that is length L. So you're going to let it go from rest. I mean, that's the idea here, that initially in these problems, that the velocity initially is 0. All right, that's important. So if that's the case, you get 0 for the kinetic energy, and potential is then mgl, that's your height. Afterwards, when it's down at the bottom, you have 1/2 mv squared, and the potential energy is 0. It's nice to let folks know where the reference is, because with potential energy, you're always free to pick the reference. So the reference is at the bottom here. That's the reference for like your MGH. So we're basically all set here. Problem's very easy to solve. The masses cancel, so you have GL equals 1/2 V squared, which means V squared is 2 GL. Look at this. You get square root of 2 GL. Now, we've done a problem like this before, and we got the square root of 2 GH. You see, it doesn't matter that it's swinging like this, because the rope has a force, a tension here, but since you're going perpendicular to the tension, you don't get messed up, because the work done by the rope, using the formula here, T dot, here this would be, a little distance. I'll say a little piece of work with a little arc length here, because let's just say we're going to go here with a little delta S, vector like that. The fact that it's 90 degrees between the two, the cosine of 90 is going to get you 0. So it's just going to change the direction. So it's the same result as dropping a ball from that height, mgl, as potential energy. You get the same result. Like before we got the square root of 2gh. It's the same thing, square root of 2gl. Then for the specific problem here with the numbers, we have 2 9.8 meters per second squared, and we have L is the 1.5 meters. Notice the dimensions are going to work out because you have meters squared and seconds squared. Take the square root, you'll get meters per second. And when you work this out, you get 5.4 meters per second. And remember, in the text, I give you intermediate steps so you can check your math as you go with the calculator. Okay, now we're ready for a solution to the general formula. And I find it helpful to draw the picture again and have the L with a little bigger angle for me to get things worked out. So here we have, this is going to come down here like that. It's going to arc down. And this is theta. This is L. And here, this distance, I'm going to break it down because if I drop it from, or let it go from here, it's not at the top anymore. So this distance here is L cosine of theta. L cosine of theta gets you that. And then here, this little part here is H, the height that I am going to release it from. That's going to be the height. But since this entire drop is L, when the L gets down at the bottom, I have the equation that the H is going to be equal to the big L minus the L cosine of theta. And this will be nice to know. L times 1 minus cosine of theta. So then when I apply my conservation of energy, I'm going to have the kinetic, and I'll go ahead and call it 1. This is position 1, and this is position 2. So 1 plus potential 1 is kinetic 2 plus potential 2. The kinetic energy is going to be 0. The potential energy now is going to be mgh, which is this thing, L, 1 minus cosine of theta. And the kinetic energy here is going to be 1/2 mv squared. And the potential energy, now that I'm at rock bottom, this one's going to be 0. So this is the equation I have. These two things are equal. And now I can see that the m, cancels out very easily. I like to bring that 2 on the other side. We got to solve for v anyway. So let's go ahead and note that the m's drop out. And when the 2 comes on the other side, I have v squared is 2 gl 1 minus cosine of theta. And here's the answer. We got the answer here as a function of the angle and other stuff. We got 2 gl 1 minus cosine of theta. So that's the general formula. That's what they wanted for the second part of the problem. Now, it's nice to just check the answer. Do we get the answer we had before when the theta is 90? Let's check. Let's check the extreme, say 90 degrees. That would mean the cosine is 90. So I would have the square root of 2 gl 1 minus the cosine of 90. And the cosine of 90 is 0. So I would get the square root of 2 gl, which is what I got earlier. So that checks. What about 0 degrees? If it's 0 degrees, it's going to go nowhere. Well, is that what we get here? Do we get that? 2 gl 1 minus the cosine of 0 degrees. Well, the cosine of 0 is 1, so 1 minus 1 is 0. Yeah, you get 0. If you just release it when you're holding it down at the bottom like that, equilibrium doesn't go anywhere. So that's kind of a nice check that these two things check out.